All right, I want to make a quick video to show you how to think about these two-body problems with proportional reasoning. Now, this applies to this problem. It also applies to, I think, a similar problem you've seen where maybe we have two boxes and something's pushing it this way. This also applies to problems like this, where we have the table and the pulley. It also applies to that we call it semi-atwood or flatwood, where we have a pulley and two boxes hanging like this. So it applies to all of these problems. All right, so if we look at this whole thing as one whole system, we can write an equation that says acceleration of the system is equal to the net force on the whole system divided by the mass of the whole system. Now, one thing to keep in mind is that we don't have friction here, and this proportional reasoning works best when we don't have friction. When we do have friction, it gets really, really messy really, really quickly, and so I wouldn't recommend using it then. But this is a good way to get an overall sense of these problems. So, if we were to just look at A. Now, A has to have the exact same acceleration as the system because it's all tied together on one whole thing. It's all moving together. So they have the same acceleration. So if we were to just look at A, you should see that A is going to have the exact same acceleration as the system. However, the mass is less. By how much? Well, A is 100 grams out of the total 150 of the system. So that is 2/3 the mass of the system. So instead of having the mass of the system down here, if we're going to look at A specifically, we now have 2/3 the mass of the system. Now the acceleration does not change, so I'm going to put a 1 there. Acceleration does not change. Now the net force then must have changed. So, oops. The net force is changing. So here, let me actually change, more clear here. Whoops, eraser, there we go. Now this is going to be mass of A and F net on A. So if the acceleration of A is still the same as the acceleration of the system, those are the same. Acceleration A, those are the same. Now our mass has gone down by 2/3. So our net force, in order to keep the same acceleration, has to go down by 2/3 as well. So, big idea, the A equals F net over M works for the system. Acceleration of A is the same as acceleration of the system. A's mass is 2/3 the system's mass. A's mass is 2/3 the system's mass. Total mass is 150. A's mass is 2/3 the system mass, so the net force on A must be 2/3 that. Now we can do the same thing, and we can do it for B. So let's change to a different color here. So if I want to know what the net force on B is, again, the acceleration of B is the same. So for B, the total mass of B is 50, and the total mass of the system is 100. So this is 1/3 the mass of the system, is what B is. Actually, this still actually should be mass of the system, because B's mass is now equal to 1/3 the mass of the system. I think you get the idea. The idea here is what's important. So the F net on B is 1/3. Okay. So what we can do is we can easily see here, since there's no friction, that this is some force F pulling the entire system to the right. Now, what we determined just now is that the net force on A is 2/3 of this force. Now, if we draw an FPD for B, since there's no friction, there is only one force on A, the force on A by B. And that is going to be the net force on A. I'm ignoring normal force and force of gravity. And so that's going to be equal to 2/3 of F. That is the net horizontal force on A, which is 2/3 the net force on the system. The net force on the system is just this pull force here. B is a little bit more complicated. B is going to feel this force to the right, F, but it's also going to feel some force backwards. A is going to be pulling it backwards on B by A. Now, this on by notation, the force on A by B, the force on B by A. Oh, hello, those are third law pairs. So we're going to mark those as equal. So now for B, we now know that this backwards force to the left is 2/3 F. We know that the force to the right here is F. So we can easily solve for, we can say, well, F to the right minus 2/3 F minus 2/3 F is going to be 1/3 F. And so the net force on B, F net on B, is equal to 1/3 that big pull force to the right, which is what we said earlier right there. So it all works. You have to kind of let yourself think about this and make sure this kind of makes sense. If you just start throwing fractions around and you do not understand this will end badly for you. But if you can see the whole picture, if you can see, oh, what's going on with A and B, what's going on with just A, what's going on with just B, this will tell you the ratio of the net forces. Notice this is 1/3 F net on, the 1/3 the net force on the system is the F net on B here. Neither of these forces on B are 1/3 anything. This tells you the net force. All right, so hopefully that helps.